Around 4.5 billion years ago, Earth began to take shape. The planet didn't form overnight. Instead, it started as a molten ball of rock and metal. The heat from the formation of the solar system kept it in a liquid state. Over time, the surface began to cool, forming a solid crust. This was the first step in Earth's long history of changes. When Earth was still a hot mass, it was a very different place from what we know today. Imagine standing on the surface of a planet where temperatures could reach thousands of degrees. There were no oceans, no forests, and no air. It was a world made of boiling lava and gases, with a thick atmosphere that likely contained hydrogen, methane, and ammonia, but not much oxygen. As the planet cooled, the surface started to solidify, forming the first solid crust. But things weren't calm. The early Earth was constantly bombarded by space debris from asteroids and comets. These collisions released a lot of energy, keeping the surface hot. Some of these impacts were so intense that they may have even caused parts of the crust to melt again. This was a chaotic time, and Earth's surface was constantly changing. The cooling of the Earth's crust eventually led to the formation of the first oceans. Water vapor in the atmosphere, likely from volcanic activity, cooled and condensed to form rain. This rain fell for millions of years, filling the low points on the surface and creating oceans. These first oceans, they were more acidic, filled with dissolved minerals and rich in gases from volcanic eruptions. During this time, the atmosphere was still thick with gases, but the amount of oxygen was very low. There was no breathable air. The surface of the Earth was constantly changing with volcanic eruptions, storms, and lightning strikes. The early atmosphere was unstable and chaotic. It was a time when Earth was far from the peaceful blue planet we see today. One of the most important things that happened during this period was the formation of the Earth's magnetic field. As the planet cooled, metals like iron and nickel sank toward the center, forming a dense core. This core, combined with the planet's rotation, created a magnetic field. This magnetic field was important because it acted as a shield, protecting the Earth from harmful solar radiation. Without it, as time passed, Earth's crust continued to change. The surface slowly cooled, and the first signs of life began to emerge. Life, though very simple, began in the oceans. Some scientists believe that life may have started with simple molecules coming together in the warm, nutrient-rich waters. These molecules formed the first building blocks of life. But it would take billions of years for life to become. The process of cooling and changing didn't stop. Earth's surface continued to shift due to the movement of tectonic plates. These plates, large sections of the Earth's crust, moved and collided over time, creating mountain ranges, earthquakes, and volcanoes. This shifting of the plates continues today, shaping the planet's surface. Over millions of years, continents began to drift apart and form. Earth was no longer just a hot, chaotic world. It started to take on a more recognizable shape. The early Earth was also a time when many of the planet's features were still developing. The oceans and atmosphere were forming, and life was slowly starting to emerge. But even with life, Earth was still very different from the planet we know today. The first creatures to inhabit Earth were simple bacteria. Like organisms, they didn't need oxygen to survive, as the atmosphere lacked enough oxygen to support more complex life. While Earth was still in its early stages, there were no dinosaurs yet. Dinosaurs didn't appear until much later, about 4 billion years after Earth's formation. But the early Earth was far from empty. The first signs of life were incredibly small, single-celled organisms that lived in the oceans. These organisms were the starting point for all life on Earth. Over time, these simple life forms evolved and changed. Some began to use the energy from the sun to create food, a process called photosynthesis. This was a game changer. As more organisms began to produce oxygen as a byproduct of photosynthesis, the atmosphere started to change. Slowly, over millions of years, oxygen levels in the atmosphere rose, making it possible for more complex life to exist. The planet, which had started as a hot molten mass, slowly became a more familiar place. The oceans settled into their current positions, and the land masses began to form. The atmosphere became more stable, and oxygen levels rose. Life evolved from simple, single-celled organisms to more complex forms, eventually leading to the dinosaurs and other creatures that would one day roam the Earth. But all of this took time. Earth's early history was marked by constant change. There were no humans, no cities, and no technology. Instead, Earth was a world of volcanic activity, shifting continents, and the slow, gradual formation of life. This was the foundation for everything that would come later, from the rise of plants and animals to the formation of the first forests and the eventual emergence of complex life. Throughout this time, Earth was slowly but surely changing. Its crust, oceans, atmosphere, and life all went through transformations. These early changes laid the groundwork for the world we know today. While dinosaurs might seem like the most iconic animals to have lived on Earth, they were far from the first. The history of Earth stretches back much further, to a time when the planet was very different from the place we know now. Around 3.8 billion years ago, life on Earth began in the simplest form possible: single-celled organisms. These early life forms were much smaller than anything we see today. They didn't have the complexity of plants or animals, but they were the foundation for everything that followed. The first life forms were likely bacteria and archaea, two groups of microorganisms that are still around today. At this time, the surface was still cooling, and the atmosphere was full of gases like methane and ammonia, but not oxygen. The oceans, formed earlier, were a rich mix of minerals, and there was no land as we know it. Life began in the oceans, where conditions were warmer and more stable. Without the protection of an atmosphere, the planet was a harsh place, bombarded by solar radiation and meteors. Still, the oceans provided a safe haven where the first life could develop. The earliest life forms were not complicated. They didn't need oxygen to survive, as there was little to be found in the atmosphere. Instead, these organisms lived by using chemicals in their environment. Some of them may have used the heat from underwater volcanic vents to fuel their processes. These vents, called hydrothermal vents, released chemicals like hydrogen sulfide, which some of the first organisms could use as food. This process, called chemosynthesis, was one of the first ways life could survive and grow. Imagine a world without sunlight, without any plants or animals. The only source of energy for these early organisms came from the chemicals in the ocean and the heat from the Earth's interior. These first microbes would have been small, simple cells that used the resources around them to survive. They didn't need sunlight like plants do today. Instead, they used the energy from the chemicals in their environment to create the molecules they needed to grow and reproduce. In those early days, life was very different from the complex ecosystems we know today. There were no plants, no animals, no trees or flowers. The only life forms were tiny microorganisms, invisible to the naked eye. Some of these organisms lived by breaking down chemicals from their surroundings, while others might have absorbed nutrients directly from the ocean. These early organisms were also very different from one another. Some were bacteria, single-celled organisms that could thrive in a wide range of environments. Others were archaea, another type of single-celled organism that could live in extreme conditions, such as hot springs or deep ocean vents. While they were both single-celled organisms, they were distinct from one another, each with its own way of surviving and growing. Despite their differences, bacteria and archaea share a key trait: they could reproduce on their own. This was an important step. Instead of needing another organism to help them reproduce, these early life forms could make copies of themselves. This allowed life to spread and evolve more quickly, eventually leading to the complex organisms. The first life forms didn't need a lot of resources to survive. They could live in the harshest environments on Earth, where other life couldn't survive. Some lived deep in the ocean, where the pressure was high and sunlight couldn't reach. Others may have lived in hot springs or near volcanic vents, where temperatures were extreme. These organisms were able to adapt to the harsh conditions of early Earth, which allowed them to thrive in places where life might have seemed impossible. Over time, these early organisms began to change. They didn't just survive, they evolved. The process of evolution, the gradual change in organisms over time, allowed life to become more complex. As these early microbes reproduced and passed on their genetic material, small changes in their DNA led to new traits and abilities. These changes allowed some organisms to survive in new environments, while others were left behind. One important change was the ability to produce energy through photosynthesis. Some bacteria began to harness the energy of the sun to make their own food. This was a major shift, as it allowed life to use the abundant energy from sunlight instead of relying on chemicals from the ocean. Over millions of years, these photosynthetic organisms released oxygen as a byproduct, slowly adding oxygen to the atmosphere. This process, called oxygenic photosynthesis, laid the groundwork for the oxygen-rich atmosphere that we rely on today. At the same time, life was not all about making food from the sun. Some early organisms continued to thrive by breaking down chemicals from the environment. These organisms didn't rely on sunlight. Instead, they lived in places where light couldn't reach, such as deep in the ocean or inside the Earth's crust. The variety of life during this time was astounding, even if it was hidden from view. These microbes found ways to survive in the most extreme places, from hot springs to icy cold lakes. The appearance of photosynthetic organisms was a turning point. While life had existed for millions of years without oxygen, the rise of these organisms changed everything. As they produced oxygen, the atmosphere slowly began to change. The early Earth had an atmosphere that didn't have much oxygen, but over time, as more and more photosynthetic organisms evolved, oxygen levels started to rise. This change paved the way for more complex life forms to evolve later on. At this point, life was still tiny and simple, but these first organisms were important. They were the first steps in the long process of evolution that eventually led to more complex forms of life. They didn't have eyes or ears or brains. They didn't move around like animals do today, but they had the ability to grow and reproduce. Over billions of years, this simple beginning would give rise to everything from tiny plants to massive whales. The earliest life forms didn't just stay in one place. As they evolved, they began to spread to new environments. Some bacteria and archaea found ways to live in new and more extreme places. They learned how to survive in environments that seemed too harsh for life to exist. This ability to adapt to new conditions helped life continue to evolve, leading to the incredible diversity of life we see today. Though the first life forms were simple, they were also highly successful. They thrived in the early oceans, adapting to changing conditions and gradually altering the planet's atmosphere. Life began to take root, and the Earth began its long transformation from a barren, rocky world to the vibrant planet we know today. These tiny, simple organisms were the first chapter in the story of life on Earth, a story that would unfold over billions of years, eventually leading to all the creatures, plants, and animals we see today. In the early stages of Earth's history, the atmosphere was very different from what it is today. It didn't contain much oxygen, and the gases that filled the air were not the same as those we breathe. Now, instead, the atmosphere was made up mostly of carbon dioxide, methane, and ammonia. These gases were released by volcanic eruptions and chemical reactions on the planet's surface. The absence of oxygen meant that the atmosphere was not breathable for any life forms that would come later. This was a time when Earth was far hotter than it is today. The early Earth was a much warmer place. Imagine a world with a thick, suffocating atmosphere and no cooling effect from the oxygen we rely on today. The planet's surface was molten, and temperatures could soar above 200 degrees Celsius. This heat came from a variety of sources, including the continuous volcanic activity, the early formation of the planet's core, and the leftover heat from the formation of the solar system. The combination of this extreme heat and a thick, unstable atmosphere created a very different environment compared to the one we know now. The lack of oxygen in the atmosphere meant that the air was toxic to many forms of life that would come later. Instead of a rich mix of gases, the early atmosphere was dominated by carbon dioxide, which is a greenhouse gas, and methane, which traps heat. Ammonia was also present, adding to the overall chemical makeup of the air. These gases created a very different kind of climate. Earth was much hotter than it is now, with temperatures high enough to keep the surface molten for millions of years. There was no breathable air, and the surface was constantly changing due to volcanic eruptions and meteor impacts. It was a harsh, unwelcoming environment. The heat from the atmosphere didn't just come from volcanic activity. The greenhouse gases like carbon dioxide and methane trapped the sun's heat close to the planet's surface. This created what we call a runaway greenhouse effect. In this early stage, the amount of heat retained in the atmosphere was far higher than it is today. While the sun's energy was still the primary source of heat, the atmosphere acted like a thick blanket, keeping the heat from escaping back into space. This resulted in a much warmer Earth. During this time, the surface of Earth was a place of constant change. Volcanic activity, storms, and meteor impacts contributed to an unstable environment. These conditions made the climate incredibly volatile. The oceans, which had formed earlier as the planet cooled, were filled with dissolved minerals and gases, giving them a much different composition from today's seas. They weren't the salty life-supporting waters we are familiar with. Instead, they were likely acidic and much warmer. This intense heat and the chemical makeup of the atmosphere had a profound effect on the planet's climate. While it was hot, it didn't mean that the Earth was uniformly warm across its surface. There were likely areas where the heat from the sun was stronger, particularly near the equator, and other areas where temperatures were cooler. But in general, Earth had a much hotter and less predictable climate compared to the one we have today. The composition of the atmosphere also played a key role in shaping Earth's early climate. The high levels of carbon dioxide and methane contributed to the greenhouse effect, causing more heat to be trapped near the surface. This meant that temperatures could stay extremely high, even though the sun's energy was not as intense as it is now. This made the early Earth much hotter than it would have been otherwise. In fact, without the thick blanket of gases, Earth might have been much colder and unable to support any life at all. This period was marked by extreme conditions. There was no ozone layer to protect the planet from harmful solar radiation. The atmosphere was thick with gases that did not support life in the way our atmosphere does today. Any life forms that existed during this time had to adapt to the harsh conditions of a planet without breathable air or stable temperatures. The first life forms, which emerged in the oceans, had to find a way to survive in this toxic, volatile environment. Over time, the Earth's atmosphere began to change. As life evolved, particularly photosynthetic organisms, oxygen began to appear in the atmosphere. This shift would eventually lead to the oxygen-rich air we now have. However, in the early stages, Earth's atmosphere was inhospitable, dominated by gases that created a harsh, unrelenting climate. The planet was far from the comfortable place we know today. The early atmosphere was not just about the gases that filled it, but also about the way the planet's climate functioned. Earth didn't have the familiar cycles of seasons that we experience now. There were no steady weather patterns or temperature shifts as we understand them today. Instead, the climate was more chaotic, driven by the unstable conditions created by the thick atmosphere and constant volcanic activity. The lack of a stable atmosphere meant that Earth's climate could change rapidly. Volcanic eruptions, for example, could release huge amounts of carbon dioxide, methane, and other gases, which would further intensify the greenhouse effect. This would make the planet even hotter for a period of time. On the other hand, the cooling of the surface could occur if certain gases were absorbed into the oceans or the atmosphere lost some of its heat. But these changes took millions of years to stabilize, and for much of Earth's early history, the climate was very unstable and far hotter than we experience today. The early Earth's atmosphere and climate were shaped by many factors, including volcanic activity, the lack of oxygen, and the thick blanket of greenhouse gases. The combination of these factors created a planet that was much hotter with a more unstable climate. As time passed and life began to emerge, the atmosphere began to change. Oxygen slowly made its way into the air, which gradually cooled the planet and made it more hospitable for life. But in the beginning, Earth was a very different place. Hot, toxic, and far from the world we live in now. The Hadean Eon, which lasted from about 4.5 to 4 billion years ago, was a time of constant change on Earth. It was a period before any life forms we recognize existed, and the planet was still forming. The Earth was a much harsher place back then. The surface was molten in many places, and volcanic activity was frequent. Meteorites and asteroids bombarded the planet, and the atmosphere was thick with gases. It was a time marked by chaos and intense heat. During the Hadean Eon, the planet was still cooling down after its violent formation. The heat from the early Earth's formation, combined with the energy from asteroid impacts, meant that much of the surface remained molten. In fact, parts of the Earth's surface were so hot that they couldn't solidify into solid rock for millions of years. Imagine a world where the ground beneath you could be liquid, and giant glowing volcanic mountains dotted the landscape. Volcanic activity played a huge role during this time. Volcanoes released gases, such as carbon dioxide and water vapor, into the atmosphere. These gases formed part of the planet's early atmosphere, which was very different from the air we breathe today. There was no oxygen. Instead, it was filled with gases like methane and ammonia. Volcanoes also shaped the Earth's surface, creating new landforms and releasing minerals that would go on to become part of the planet's crust. While the Earth's surface was still in the process of cooling and solidifying, asteroid impacts were another major event. These impacts were frequent during the Hadean Eon, a result of the chaotic environment of the early solar system. As asteroids and comets collided with Earth, they caused massive explosions, releasing heat and sometimes even melting parts of the planet's crust. These impacts helped shape the Earth, but they also meant that the planet's surface was constantly being reshaped. Imagine the Earth being bombarded by these asteroids and comets. These objects were much more common in the early solar system than they are today. Every time one of these bodies hit the planet, it released massive amounts of energy. Some impacts would have been so intense that they created temporary, molten lakes on the surface. As the planet cooled, the surface began to solidify, but the constant impact kept it in a state of flux. Despite the frequent volcanic eruptions and asteroid strikes, there was some order to the chaos. As the Earth slowly cooled, it began to form a crust. This crust wasn't like the solid surface we walk on today. It was thin and fragile. It would be broken apart by volcanic activity and asteroid impacts, only to be replaced by new crust as the cooling process continued. This cycle of destruction and renewal helped shape the Earth's surface over millions of years. As the planet's crust slowly formed, it created the first solid land masses. These land masses were small and not the large continents we are familiar with now. They were made up of the earliest rocks, which were formed from the cooling lava that flowed from volcanoes. Over time, these small landmasses grew and combined, forming larger pieces of Earth's crust. However, these early landmasses were not stable for long. They were constantly being reshaped by volcanic activity and asteroid impacts. The oceans also began to form during the Hadean Eon. Water vapor, released from volcanic eruptions, began to cool and condense in the atmosphere. This created the first rain, which fell to the surface and filled the low-lying areas, forming oceans. However, these early oceans were not the same as the ones we have today. They were likely very hot, filled with minerals, and not capable of supporting life just yet. The conditions were still too harsh for anything other than the most basic forms of life to survive. The Earth's atmosphere during the Hadean Eon was very different from what it is now. It was thick with gases like methane, ammonia, and carbon dioxide, and it didn't contain any oxygen. This meant that there was no breathable air, and no life could have survived on land. Instead, the planet's surface was a hostile place. Without any protection from the Sunday's radiation, life would not have been able to thrive. The lack of oxygen in the atmosphere also meant that the planet's climate was much hotter than it is today. This period of constant change eventually gave way to more stability as the Earth began to cool further. As the surface solidified and the planet's crust became more stable, conditions began to improve. The constant volcanic eruptions and asteroid impacts slowed down, and the planet's surface started to take on a more familiar shape. But this process took millions of years. The Earth went through countless cycles of change during the Hadean Eon, and it was a time of upheaval. Despite the harsh conditions, the Hadean Eon laid the groundwork for the planet we know today. The volcanic activity that released gases into the atmosphere eventually set the stage for the formation of the oxygen-rich air we breathe. The asteroid impacts, though destructive, helped shape the Earth's surface and provided some of the minerals needed for life, and the formation of the planet's crust provided the foundation for the continents and oceans that would come later. Even though life did not exist during the Hadean Eon, the period was crucial for creating the conditions necessary for life to emerge. The volcanic activity, asteroid impacts, and the formation of Earth's crust were all part of a larger process that would lead to the development of life. As the planet cooled and stabilized, life would eventually begin in the oceans, setting the stage for the next chapter in Earth's history. The Hadean Eon was a time of great change and chaos, but it was also a time of growth. The planet's surface was constantly being reshaped, and the conditions for life were slowly being set in place. Earth was still a long way from the world we know today, but it was taking its first steps toward becoming the planet we live on now. After the tumultuous Hadean Eon, Earth entered the Archean Eon, which lasted from about 4 to 2.5 billion years ago. During this time, Earth began to settle into a more stable environment. The surface cooled further, and the first solid landmasses began to form. While the planet was still very different from what we know today, it was a time of significant change. The first stable continental landmasses took shape, and the earliest life forms began to emerge. During the Archean, the Earth's surface was more solid than before, but it was still not the comfortable planet we think of now. The landmasses that formed were small compared to the continents we have today, but they were important. These first landmasses were the foundation for the Earth's future continents. They were made up of the earliest types of rocks, formed by the cooling of the molten Earth. These landmasses were constantly changing, shaped by volcanic activity and shifting tectonic plates. Despite the growing stability of the surface, Earth was still an incredibly hot place. The atmosphere, though changing, was still not breathable, and the air was thick with gases like carbon dioxide and methane. There was still no oxygen in the atmosphere, and life, if it existed at all, had to find ways to survive in harsh conditions. The planet was still too hostile for complex organisms, but simple life forms were starting to make their mark. One of the most important developments during the Archean eon was the rise of life. The earliest life forms were microscopic, single-celled organisms. They didn't resemble the plants and animals we know today, but they were the first step toward more complex life. These early organisms were mostly bacteria, and some of them were capable of photosynthesis. They used sunlight to create energy, which was a huge shift in how life on Earth functioned. Among the most well-known of these early life forms were stromatolites. Stromatolites are structures created by layers of bacteria that form in shallow water. As these bacteria photosynthesized, they released oxygen into the water. The layers of bacteria trapped minerals from the surrounding water, creating these rock-like formations. Stromatolites were the first evidence of life interacting with the environment in a way that left a permanent mark on the planet. These structures show how early life was shaping the Earth, even though the atmosphere itself was still mostly free of oxygen. Photosynthesizing bacteria were critical to this early stage of life. They used sunlight, carbon dioxide, and water to create food, a process that also released oxygen as a byproduct. While the amount of oxygen released during the Archean eon was small compared to what we have today, it was an important first step in changing the composition of Earth's atmosphere. These bacteria were slowly beginning to fill the planet with oxygen. Although it would take billions of years for the oxygen levels to reach the levels needed to support complex life, the rise of these simple photosynthesizing organisms had a profound impact on the Earth. Over time, their activity began to slowly change the atmosphere, setting the stage for the future of life. As the bacteria released oxygen into the oceans, the first small amounts of oxygen began to accumulate in the atmosphere. This was a slow process, but it was a critical one. Even though the oxygen levels were still low, it marked the beginning of a significant transformation. At the same time, Earth's surface was continuing to change. Volcanic activity continued to shape the landmasses, and tectonic plates were beginning to move in a way that would eventually form the continents we recognize today. These tectonic shifts caused the land to break apart and reassemble, creating new seas, mountains, and valleys. While the Earth was still volatile, the movement of tectonic plates brought a sense of order to the planet's surface. Earth was also slowly cooling during the Archean. The planet's surface had been very hot in the Hadean. But by the time the Archean eon began, it was beginning to stabilize. The molten surface had solidified, and the first continental landmasses were able to form. This cooling allowed more stable environments to develop, and it provided a foundation for the growth of life. Still, the climate was far from the mild conditions we experience today. The planet was much hotter, and the atmosphere was thick with gases that made it inhospitable to most forms of life. Life during the Archean was still very simple. There were no plants or animals. Instead, bacteria and other single-celled organisms dominated the Earth. These organisms thrived in the oceans where the conditions were more stable. Life was still confined to the water, as the land was too harsh for organisms to live on. The oceans were warm, full of minerals, and rich with chemicals from volcanic activity. These chemicals were important for life, providing the building blocks needed for organisms to grow and reproduce. The Archean eon was a time when life was beginning to have an impact on the planet. Although the atmosphere was still far from the oxygen-rich air we breathe today, the photosynthesizing bacteria were slowly changing it. Their ability to produce oxygen set the stage for future developments, even if the oxygen levels remained very low. These early organisms left their mark on the planet through the formation of stromatolites, the first evidence of life interacting with the environment. Throughout the Archean eon, life continued to evolve, and the Earth continued to change. The landmasses grew larger, volcanic activity slowly decreased, and the atmosphere began to shift. While life was still small and simple, the foundations were being laid for the more complex life forms that would come later. The Archean was the beginning of a long process, that would eventually lead to the rich and diverse world we live in today. In the end, the Archean eon was a time of great change. The Earth's surface cooled and the first land masses formed. Life began to evolve, starting with simple bacteria that shaped the planet through photosynthesis. Though the Earth was still a very different place from what it is today, the Archean set the stage for the complex ecosystems and varied life forms that would follow. The Proterozoic eon, which lasted from 2.5 billion to 541 million years ago, was a time of significant change on Earth. One of the most important events of this period was the buildup of oxygen in the atmosphere, an event often called the Great Oxygenation Event. This was the first major increase in oxygen levels, and it fundamentally altered the planet. For much of Earth's history, the atmosphere had been mostly made up of gases like carbon dioxide, methane, and ammonia. There was little to no oxygen, but over time, tiny organisms began to produce oxygen. And this started to change everything. For billions of years before the Proterozoic, life on Earth existed without oxygen. The early organisms that lived in the oceans were mostly bacteria. These bacteria didn't rely on oxygen for energy. Instead, they used other chemicals to survive, and the oceans were full of them. This period, known as the Archean, set the stage for the Proterozoic, but didn't see much oxygen in the air or water. The big shift came when photosynthesizing bacteria, like cyanobacteria, began to release oxygen into the oceans. Cyanobacteria are simple organisms that, through photosynthesis, turn sunlight, carbon dioxide, and water into food. As a byproduct, they released oxygen. At first, this oxygen didn't accumulate in the atmosphere. Instead, it dissolved into the oceans. The oceans were capable of holding much of the oxygen because of the large amount of dissolved iron and other elements in the water. Over time, the amount of oxygen in the oceans grew as more and more cyanobacteria produced oxygen. Some of it began to build up in the atmosphere. This was a slow process, but by about 2.4 billion years ago, the Great Oxygenation Event began in full force. The release of oxygen caused a dramatic shift. It was the first time in Earth's history that oxygen began to accumulate in the atmosphere in any significant amount. This change was not gradual. It was more of a slow build-up over millions of years. However, when the oxygen levels rose enough, the planet entered a new phase. Before this oxygen build-up, Earth was a very different place. The atmosphere was thick with gases that were not breathable for most of the life forms we know today. The Earth was much hotter, and its surface had different conditions. The oceans were rich with chemicals, and life was simple, mostly made up of single-celled organisms. Oxygen was toxic to many early life forms, which had evolved to live without it. As oxygen began to build up, it started to cause a shift in the environment, and many of these early organisms could no longer survive in the new conditions. Some life forms, however, began to adapt to the presence of oxygen. The rise of oxygen had far-reaching effects. It didn't just change the atmosphere, it also changed the chemistry of the oceans and the land. As oxygen became more abundant, it reacted with minerals in the oceans and on land. This led to the formation of oxidized minerals, which were not common before the oxygen buildup. One of the most well-known results of this process was the formation of banded iron formations in the oceans. These formations were created when oxygen reacted with iron dissolved in seawater, creating solid iron that settled to the ocean floor. At the same time, life was beginning to adapt to this new atmosphere. Some organisms evolved the ability to use oxygen to produce energy, a process called aerobic respiration. Aerobic respiration is much more efficient than the anaerobic methods used by earlier life forms. It allowed organisms to get more energy from the same amount of food. This gave those that could use oxygen a survival advantage. The Proterozoic wasn't just about the buildup of oxygen, it was also a time when life began to become more complex. The first multicellular organisms began to appear, although they were still quite simple compared to modern plants and animals. The Proterozoic saw the emergence of early eukaryotes, which are cells with a nucleus. These were a big step up from the simpler prokaryotic cells, like bacteria, which lacked a nucleus. Around 1.6 billion years ago, the first known multicellular life forms began to evolve. These organisms, though simple, laid the groundwork for the much more complex forms of life that would appear later. The rise of multicellularity was one of the key steps toward the plants, animals, and fungi that would eventually populate the Earth. As the Proterozoic continued, the planet's conditions continued to shift. The atmosphere became richer in oxygen, and the Earth's surface cooled. This cooling allowed the planet to settle into a more stable state. By the end of the Proterozoic, the planet was on the verge of a new phase in its history. The increase in oxygen had set the stage for more complex forms of life. The rise of eukaryotes, the emergence of multicellularity, and the buildup of oxygen would all play critical roles in the next stage of Earth's history. The Phanerozoic, when plants, animals, and eventually humans would appear. The Proterozoic was also marked by some other important events. One of these was the formation of supercontinents. The Earth's tectonic plates were slowly shifting, and by the end of the Proterozoic, large landmasses had formed and broken apart several times. These supercontinents, though temporary, had a major impact on the Earth's climate and environment. They influenced ocean currents, weather patterns, and the distribution of life. The Proterozoic saw dramatic changes in the planet's environment, driven by the rise of oxygen and the evolution of life. The oxygenation of the atmosphere and oceans was a crucial event in Earth's history. It not only changed the way life interacted with the environment, but also set the stage for the more complex life forms that would follow. By the end of the Proterozoic, Earth was ready for the explosion of life that would come in the Phanerozoic eon. During the Proterozoic eon, Earth's surface was far from the stable continents we know today. Instead, the planet's land masses were constantly shifting and changing. One of the most significant geological events during this time was the formation of the supercontinent Rodinia. Rodinia wasn't a single landmass that stayed in place for long periods. Instead, it formed and broke apart over millions of years, shaping the planet's geology long before dinosaurs appeared. Rodinia began to take shape around 1.3 billion years ago. It was a large landmass, formed by the collision of smaller continents. These smaller pieces of land were pulled together by the movement of tectonic plates, the large pieces of Earth's crust that float on the more fluid mantle beneath them. The movement of these plates caused the land masses to collide and fuse, creating Rodinia. It was not the first supercontinent to form on Earth, but it was one of the largest and most well-known of the Proterozoic. Imagine Earth's surface as a giant jigsaw puzzle, with pieces slowly drifting toward one another. Over time, these pieces would collide and merge, forming the supercontinent. Rodinia brought together land masses from all over the planet, creating a single massive continent. This formation affected Earth's climate and environment in many ways. The existence of a supercontinent, like Rodinia, altered the planet's weather patterns. As the landmasses came together, the climate changed. Large landmasses can affect weather by influencing air currents and ocean circulation. With a large continent in the center of the Earth, the climate could become more extreme. The regions near the equator could be very hot, while areas farther from the equator might experience cold temperatures. The interior of the continent would have been much drier, and its coastal areas would have seen different weather patterns. One of the major effects of the supercontinent was on Earth's oceans. The formation of Rodinia caused changes in ocean currents and the distribution of water around the planet. The large landmass blocked the movement of water between oceans, leading to the creation of shallow seas. These seas were important for the development of life, as they provided an environment where early organisms could evolve. But at the same time, the closure of certain ocean passages could have led to environmental stresses, such as changes in the composition of seawater. Rodinia's formation was not a permanent state. Like other supercontinents, it didn't last forever. Over millions of years, the supercontinent began to break apart. The tectonic plates that had formed it started to move again, pulling the land masses apart. This process of rifting, or the breaking apart of continents, is a natural part of the planet's geological cycle. As the pieces of Rodinia separated, they started to drift apart, creating new oceans and altering the planet's geography once more. This breaking apart didn't happen all at once. The process was gradual and took millions of years. The land masses that once formed Rodinia began to split, and new oceans began to form between them. The rifting of Rodinia was part of a cycle that would continue throughout Earth's history. As Rodinia broke apart, new land masses would eventually come together to form new supercontinents, a process that continues even today. The breakup of Rodinia had a significant impact on Earth's geology. It led to the creation of new ocean basins, which in turn affected the planet's climate. As the land masses spread out, they created new coastlines and increased the complexity of Earth's geography. This process of continental drift, where land masses move across the surface of the Earth, would go on to shape the planet's surface in the following eons, including the formation of the continents we recognize today. The rifting of Rodinia also contributed to volcanic activity. As the continents pulled apart, magma from the Earth's mantle rose to the surface. This caused volcanic eruptions, which added new material to the Earth's crust. The volcanic activity also released gases into the atmosphere, such as carbon dioxide, which affected the planet's climate. Volcanic eruptions can have short-term cooling effects, but over the long term, they can contribute to global warming by releasing greenhouse gases. The process of Rodinia forming and breaking apart also affected life on Earth. The Proterozoic was a time when simple, single-celled organisms were the dominant form of life. But the changes in the planet's geography and climate during the time of Rodinia's existence would have influenced the environment in which these organisms lived. The shifting of land masses could have created new habitats, leading to new opportunities for life to evolve. At the same time, the changing climate and ocean currents may have posed challenges for life, influencing how organisms adapted to their surroundings. The movement of tectonic plates also had an impact on Earth's atmosphere. As Rodinia began to break apart, volcanic activity increased, releasing gases that contributed to the atmosphere's composition. This volcanic activity was one of the main sources of carbon dioxide and other gases that contributed to Earth's greenhouse effect. These gases would have affected the planet's climate, making it warmer and influencing the conditions under which life evolved. Throughout the Proterozoic, Rodinia's formation and breakup were just one part of Earth's constantly changing geological landscape. The shifting land masses created new oceans, new coastlines, and new environmental conditions that affected both the climate and the evolution of life. The rifting of the supercontinent was not just a geological event, it was a process that helped shape the world we live in today. As Rodinia broke apart and new land masses drifted away from each other, Earth's surface became more complex. The process of continental drift continues to this day, constantly reshaping the planet's geography. The legacy of Rodinia, though it no longer exists, is still visible in the way the continents are arranged today. The breakup of this supercontinent set in motion the long-term changes that would eventually lead to the continents we now see. Around 1.6 billion years ago, life on Earth took a significant step forward. Up until that point, all living organisms were single-celled, meaning each cell worked on its own to survive. But during this time, the first multicellular life forms began to emerge. These early multicellular organisms were simple, but their appearance marked a turning point in the history. The earliest multicellular life forms were not complex animals or plants. They were simple organisms like algae and early forms of sponges. These life forms were still very basic compared to the plants and animals we know today, but they represented a big leap from the single-celled organisms that had dominated the planet for so long. The transition from single-celled to multicellular life wasn't a sudden change. It happened over a long period of time. The first multicellular organisms were likely groups of cells that began to stick together and work together. In single-celled organisms, each cell does everything on its own. It gathers food, produces energy, and reproduces. But in multicellular organisms, cells began to specialize. Some cells focused on one job, like gathering food, while others specialized in reproduction or protecting the organism. This division of labor allowed these early organisms to grow larger and more complex. Zone of the first examples of multicellular life were simple algae. Algae are photosynthetic organisms that can live in a wide variety of environments, from the ocean to freshwater lakes. Some of the earliest forms of algae were likely single-celled, but over time, groups of these cells began to form simple structures. These structures allowed the cells to work together, using sunlight to create energy through photosynthesis. Over millions of years, these simple algae would evolve into more complex forms, but their basic structure remained relatively simple during this early period. Along with algae, the first forms of simple multicellular animals, like early sponges, began to appear. Sponges are one of the simplest types of animals, made up of a collection of specialized cells that work together. These early sponges were likely small and simple, but they represent one of the earliest examples of animal life that was not made up of just a single cell. The cells in these early sponges worked together to filter food from the water, and they had some level of organization that allowed them to function more efficiently than single-celled organisms. The rise of multicellular life marked the beginning of new possibilities for life on Earth. By working together, cells in multicellular organisms could perform more specialized tasks, leading to greater efficiency. This allowed these organisms to grow larger and take on more complex forms. However, this growth also created new challenges. Larger organisms needed more resources to survive, and their cells had to find ways to work together more effectively to ensure survival. For example, as multicellular organisms grew, they had to develop systems to transport nutrients and waste throughout their bodies. In simple single-celled organisms, nutrients could diffuse directly into the cell and waste could diffuse out. But in larger, multicellular organisms, cells located farther from the surface needed a way to get food and remove waste. Over time, simple structures like channels and specialized cells evolved to transport nutrients and waste throughout the organism. This shift to multicellularity also required more complex ways of communication between cells. In a single-celled organism, all the work is done by one cell, so it doesn't need to communicate with other cells. But in a multicellular organism, the cells need to coordinate with each other to ensure the organism functions properly. This led to the development of signaling systems which allowed cells to communicate and work together more effectively. Despite these challenges, multicellular life forms began to spread and evolve. As time passed, these early multicellular organisms became more diverse. Some evolved to live in the oceans, while others began to move into freshwater environments. Over millions of years, multicellular life forms grew in size and complexity. Some began to develop more advanced features, like the ability to move or sense their environment. These advances laid the foundation for more complex life forms to evolve in the future. In the oceans, multicellular algae began to evolve into more complex forms. These algae were not only important because they could photosynthesize, but also because they formed the base of many early food chains. Other organisms relied on these algae for food, and over time, more complex food webs began to form in the oceans. Some multicellular life forms, like early sponges, began to evolve more specialized feeding systems, allowing them to filter more food from the water. These early organisms played a crucial role in shaping the ecosystems that would follow. While multicellular life forms were still relatively simple during this time, their appearance marked a turning point. The fact that cells could work together and specialize set the stage for even more complex life forms in the future. By the time multicellular organisms had evolved into more complex creatures, life on Earth had already begun to change in ways that would allow for the evolution of animals, plants, and fungi. The rise of multicellularity opened the door for all the complex life forms we are familiar with today. One important example of this transition is seen in the development of multicellular plants. While early plants were likely simple and single-celled, the evolution of multicellularity allowed plants to grow larger and more complex. These early plants were still very simple, but they were the first steps toward the trees, flowers, and other plants we see today. The development of multicellular life forms was not just a step forward for one type of organism. It had a ripple effect across Earth's ecosystems. The ability to specialize and work together allowed life forms to occupy new niches and fill new roles in the environment. As multicellular organisms became more common, they changed the way the Earth's ecosystems functioned, making way for the complex interactions that would later lead to the rise of animals, plants, and fungi. Looking back, the rise of multicellular life forms around 1.6 billion years ago was a critical moment in the history of life on Earth. These early organisms paved the way for the complex, diverse life forms that would eventually emerge. Though simple by today's standards, they were the foundation for the variety of life that would follow. The transition to multicellularity set the stage for all the life we recognize today. Around 700 million years ago, Earth went through an extreme period known as Snowball Earth. During this time, the planet experienced dramatic ice ages, and scientists believe that almost the entire surface was covered in ice. This was a time when Earth's climate was much colder than it is today, and the ice reached as far as the equator. The idea of Snowball Earth suggests that the planet's temperature dropped to the point where ice sheets formed everywhere. It wasn't just the poles that were frozen, even tropical regions near the equator were covered in ice. Imagine a world where the oceans and land masses were all encased in thick ice, stretching from the poles to the equator. It was a global ice age that lasted for millions of years, an event that completely changed the planet's environment. The cause of Snowball Earth is still debated, but there are a few ideas that scientists believe could explain this extreme cooling. One possibility is that the amount of carbon dioxide in the atmosphere dropped significantly. Carbon dioxide is a greenhouse gas that traps heat, so with less of it, the Earth would have cooled. Another possible reason is that the planet's position relative to the Sunday could have shifted. If Earth was farther from the Sunday, or had a weaker solar output, it would have been colder, making it easier for ice to form and spread across the planet. The cooling of the Earth likely began with the formation of ice sheets at the poles. Once ice started to form in high latitudes, it would reflect more sunlight, making it even colder. This is called the albedo effect. With more ice on the surface, more sunlight was reflected away, which made the planet even cooler, creating a cycle that allowed the ice to spread further. Eventually, this led to the formation of ice in areas that were once too warm, such as near the equator. At the time of Snowball Earth, life on Earth was still very simple. Most life forms were single-celled organisms living in the oceans. The thick ice that covered much of the planet would have made it difficult for these organisms to survive. The ice would have blocked out sunlight, reducing photosynthesis, the process that most early life forms relied on for energy. Without sunlight, life would have struggled, and many organisms likely went extinct. However, not all life on Earth was wiped out. Scientists believe that some life forms managed to survive in small pockets of open water. These pockets of liquid water would have been trapped beneath the ice, where life could still thrive in the absence of sunlight. These areas may have been heated by volcanic activity or geothermal energy from the Earth's interior. The survival of life in these small, isolated regions may have been crucial for the recovery of life after the ice eventually began to melt. The end of Snowball Earth is just as mysterious as its beginning. Over millions of years, the Earth slowly began to warm again, possibly due to volcanic activity. Volcanic eruptions release carbon dioxide and other gases into the atmosphere, which can trap heat and gradually warm the planet. As the temperature increased, the ice slowly began to melt, and the Earth returned to a more temperate climate. This thawing process would have taken a long time, but once it began, the ice began to recede, and life started to recover. The warming of the planet after Snowball Earth was likely a gradual process. As the ice melted, it would have released fresh water into the oceans, possibly affecting ocean currents and ecosystems. The change in climate may have created new environments where life could flourish once again. This period marked the beginning of a new chapter in Earth's history, as the planet began to warm up and more complex life forms began to evolve. While the Snowball Earth event was an extreme and dramatic period in Earth's history, it had a lasting impact on the planet. The dramatic climate shift changed the planet's geology, atmosphere, and ecosystems. After the ice melted, life began to recover, eventually leading to the rise of more complex organisms. It is possible that the Snowball Earth event played a role in shaping the evolution of life, providing an opportunity for new life forms to emerge and evolve. Alpha Snowball Earth is a fascinating period in Earth's history. It also raises important questions about the Earth's climate system and how it can change. The event shows just how sensitive Earth's climate can be to changes in atmospheric gases and other factors. It also shows the resilience of life, as simple organisms found ways to survive even in the harshest conditions. The recovery from Snowball Earth may have helped set the stage for the evolution of more complex life, ultimately leading to the rise of animals, plants, and eventually humans. About 541 million years ago, Earth experienced a remarkable event known as the Cambrian explosion. This was a period of rapid change in the history of life on Earth. It marked a time when many new and diverse forms of life appeared in a relatively short span. Before the Cambrian explosion, life on Earth was mostly simple, made up of single-celled organisms and some multicellular life forms that were still quite basic. But during the Cambrian explosion, life diversified at an astonishing rate, especially in the oceans. This period laid the groundwork for much of the life that would follow, including animals with hard bodies and more complex structures. At the start of the Cambrian period, most life forms were soft-bodied and lacked the hard protective shells or skeletons we see in many animals today. The oceans were teeming with simple creatures, but these organisms were small and mostly soft, which made it hard for them to leave a lasting impression in the fossil record. During the Cambrian explosion, however, many of these early animals began to evolve hard parts, such as shells, exoskeletons, and bones. These hard bodies not only provided protection, but also made it easier for the organisms to leave fossils that could be studied by scientists millions of years later. One of the major developments during this time was the appearance of early marine animals. These animals included some of the first arthropods, which are the group of animals that includes insects, spiders, and crustaceans, as well as the first early chordates, the ancestors of vertebrates, including fish, and eventually land animals. These animals had more advanced features, such as segmented bodies, jointed limbs, and eyes, and their emergence set the stage for the later development of more complex life forms. The oceans during the Cambrian were full of strange creatures. Some of the most notable early forms of life were trilobites, an extinct group of arthropods. Trilobites were among the first animals to develop hard exoskeletons, which provided both protection and structure. Their bodies were segmented, and they had complex eyes, allowing them to navigate and detect movement in the water. Other early life forms included the first mollusks, such as snails and clams, which also developed hard shells for protection. Alongside these familiar creatures, there were many other organisms that seem strange to us today. For instance, there were creatures with soft bodies, but hard mineralized structures that helped them survive. These included early forms of sponges and cnidarians, like jellyfish. These organisms did not have the complex features we associate with animals today, but they played a key role in the ecosystems of the Cambrian seas. One of the most significant features of the Cambrian explosion was the rapid rate at which new species evolved. The fossil record shows a sudden increase in the number of different life forms, with many major groups of animals appearing within a relatively short period of time. This burst of diversification is sometimes compared to the rapid growth of life forms during other periods, such as the development of flowering plants or the rise of mammals. However, the Cambrian explosion is particularly important because it marks the first time that complex, multicellular animals with specialized body parts appeared in such variety. This diversification wasn't limited to the development of hard bodies. The Cambrian explosion also saw the emergence of new feeding strategies, such as predation. Many animals began to evolve features that allowed them to capture and consume other organisms. This led to a dramatic change in the dynamics of early ecosystems. Prior to this, most life forms were either filter feeders or grazers, eating microscopic organisms or plant material. But with the rise of predators, the food chain began to take shape, and ecosystems became more complex. The increase in complexity wasn't just in terms of body parts. Some animals developed more advanced systems for movement and sensing their surroundings. For example, many of the arthropods that appeared during this time had compound eyes, which gave them a wider field of view and the ability to detect movement more effectively. Other creatures developed more efficient ways of moving through the water, such as swimming with the use of fins or using flexible, segmented bodies for better mobility. In the early days of the Cambrian, life was still mainly confined to the oceans. The land remained barren, with no plants or animals to be found on solid ground. But the oceans were full of life, and they became the center of evolution during this time. As the new marine animals evolved and diversified, they began to fill the different ecological niches available in the seas. Some adapted to live on the ocean floor, while others became free swimming predators. This diversification of life in the oceans laid the foundation for the more complex ecosystems that would eventually emerge in other environments, including land. The Cambrian explosion didn't just change life forms, it also changed the way life interacted with the environment. The appearance of hard bodies, specialized body parts, and new feeding strategies created more competition and allowed for a wider range of evolutionary experiments. Animals were now more capable of surviving in a variety of environments, from the ocean depths to the surface, and their relationships with each other became more intricate. After the Cambrian explosion, life on Earth continued to evolve and diversify. The changes that occurred during this period were fundamental in shaping the direction of future evolution. Many of the basic body plans and strategies that emerged during this time would be refined and adapted in the following millions of years, leading to the vast diversity of life that would eventually occupy the planet, from land-dwelling vertebrates to the vast array of marine life we know today. In the fossil record, the Cambrian explosion is marked by a sudden increase in the number of species, as well as the appearance of many new body plans and features. While not every new form of life from this period survived, many of the animals that evolved during the Cambrian became the ancestors of later life forms. The Cambrian explosion was a key turning point in the history of life on Earth, as it set the stage for the evolutionary developments that would follow. Life in the Cambrian seas was like a bustling, dynamic world, where new creatures evolved rapidly, filled ecological niches, and adapted to the changing environment. The emergence of hard-bodied animals, such as trilobites and mollusks, along with the first predators and complex feeding strategies, changed the course of evolution and made way for the even greater diversity of life that would follow in the coming eras. The Cambrian explosion was a crucial time when Earth's oceans were transformed into a thriving, complex ecosystem, setting the foundation for the later evolution of more advanced life forms. Before land animals like dinosaurs appeared, Earth's biosphere was dominated by life in the oceans. The seas were teeming with a wide variety of creatures, ranging from early invertebrates like trilobites to soft-bodied animals that lived in the depths and along the shores. Life in the oceans during this time was vibrant and diverse, though it looked very different from the world we know today. In the early stages of Earth's history, the oceans provided a safe environment where life could thrive. The waters were filled with single-celled organisms, and later, multicellular life began to emerge. These early marine life forms were often soft-bodied and small, but some developed hard outer shells, which provided protection from predators and harsh environmental conditions. Over time, life in the oceans began to diversify, creating complex ecosystems where different species interacted with one another. One of the most well-known creatures from early ocean life was the trilobite. These arthropods were among the first animals to develop hard exoskeletons, providing protection and allowing them to survive in a variety of environments. Trilobites were one of the most successful early invertebrates, appearing in the Cambrian period and lasting for millions of years. Their hard outer shell helped them avoid predators, and they had many different body shapes and sizes. Some species were small, while others grew quite large. Trilobites scuttled along the ocean floor, feeding on smaller organisms, while others swam through the water in search of food. Their presence in the oceans was a sign of the rapid diversification of life during this period. Alongside trilobites, other early marine invertebrates began to emerge. Soft-bodied animals like sponges and cnidarians, which include jellyfish and corals, filled the oceans. These creatures didn't have the hard outer shells or exoskeletons of trilobites, but they played an important role in the ecosystems of the seas. Sponges, for example, acted as filters, filtering water to gather food particles. Cnidarians, such as jellyfish, relied on their tentacles to capture prey and defend themselves. Although they lacked the hard bodies of arthropods, they were still highly effective at surviving and finding food. The oceans were not just full of small invertebrates, they also hosted some of the earliest predators. These predators were often larger than their prey and had developed specialized features to capture and eat other creatures. One of the first large predators in the oceans was the Anomalocaris, a strange early arthropod. It had a long body and a pair of large, grasping appendages that it used to catch prey. The Anomalocaris had a pair of compound eyes, which gave it excellent vision, making it an effective hunter. It was just one example of how the oceans were evolving into more complex ecosystems where different species began to play different roles, from prey to predator. While the oceans were teeming with life, the ecosystems were still much simpler than those that would later develop on land. The creatures living in the oceans were mostly invertebrates, and the food chains were shorter. Early life forms, including simple algae and plankton, were the base of the food web. Larger animals fed on these smaller organisms, and the predators at the top of the food chain helped regulate the populations of other species. Life in the oceans was not without its challenges. The waters were sometimes harsh, with changing temperatures, currents, and availability of food. Despite these challenges, the oceanic environment provided many advantages. The water offered protection from extreme temperature changes, and the oceans were rich in nutrients. Life in the seas evolved to take advantage of these conditions, leading to the development of various feeding strategies and survival tactics. Some creatures developed the ability to move efficiently through the water. For example, early fish evolved streamlined bodies and fins that allowed them to swim faster, helping them escape predators or chase down prey. These fish were important in the oceans, as they were able to occupy new ecological niches by feeding on smaller organisms or becoming prey for larger animals. The development of swimming and the appearance of fish marked another major step in the evolution of marine life, as it opened up new ways for organisms to interact with their environment. While life in the oceans was flourishing, the land remained largely barren. There were no plants or animals on land, and the harsh conditions made it difficult for life to take hold on solid ground. The oceans, with their stable temperature and abundant nutrients, provided the ideal environment for life to evolve and diversify. Over time, marine life grew more complex, leading to the appearance of new species that filled different ecological niches. The oceans also provided an environment where life could develop and interact in more complex ways. Some species evolved to live in symbiotic relationships, where two or more species work together to survive. For example, certain types of marine animals, such as some species of fish and cleaner shrimp, formed partnerships where one species would clean parasites off the other. These relationships were beneficial to both parties and helped maintain balance in the ecosystem. While the oceans were rich with life, Earth's surface was still quite different from the world we know today. The first continents were beginning to form, and volcanic activity was shaping the landscape. However, life on land was still in its early stages. The oceans remained the dominant environment, with most life confined to the seas. It would take millions of years before animals and plants began to move onto land. But the oceans were where life first flourished. As life continued to evolve in the oceans, the variety of organisms grew. Some species began to develop more advanced features, such as better senses or stronger defenses against predators. The ocean ecosystems became more diverse, with different species occupying different niches, from the bottom-dwelling creatures like trilobites to the free-swimming predators like Anomalocaris. The oceans were home to a wide range of life forms that would help shape the future of life on Earth. The oceans during this time were not just a place of survival, they were a place of evolution. The creatures living in the seas adapted to their environment, developed new features, and interacted in complex ways. The seas provided the conditions necessary for life to evolve and diversify, setting the stage for the later appearance of more complex life forms on land. Before dinosaurs roamed the Earth, the oceans were already home to thriving ecosystems, where marine life was already well on its way to shaping the future of life on Earth. The first vertebrates appeared during the late Cambrian period, marking a crucial moment in the evolution of life on Earth. Vertebrates are animals with backbones, a feature that sets them apart from other life forms. These early vertebrates were simple fish, but they were the foundation for all future animals with backbones, including land-dwelling creatures like amphibians, reptiles, birds, and mammals. The first fish were small and relatively simple compared to the animals we know today. They had a backbone made of cartilage, a flexible material that would later be replaced by bone in many species. These early fish were part of a larger group of organisms called chordates, which share the basic feature of having a notochord, a flexible rod that supports the body. Over time, the notochord would evolve into a more rigid backbone, but at this point, it was still an important part of the animal's body structure. These early fish didn't have the complex features of modern fish, like jaws or specialized fins. Instead, they had simple structures that allowed them to swim in the ocean and filter small particles of food from the water. They lived in the seas, which were teeming with a variety of other life forms, including invertebrates and other simple organisms. The oceans at this time were a very different environment from what we see today, filled with strange and unfamiliar creatures. The appearance of vertebrates, however, was a major step in the evolutionary process. Backbones offered more support and protection compared to the soft bodies of invertebrates. This allowed the fish to grow larger and develop more complex features over time. With a backbone, these early vertebrates could have a more structured body, which made movement more efficient and allowed for better control of their position in the water. This advantage would help fish survive and thrive, leading to the wide variety of vertebrates that would appear in the future. These early vertebrates also had a rudimentary nervous system that allowed them to respond to their environment in more advanced ways than invertebrates. The backbone provided a structure for the spinal cord, which is a key part of the nervous system. This allowed the fish to coordinate their movements and react to external stimuli, such as changes in light or the presence of predators. This early nervous system was an important step in the development of more complex brains and behaviors that would come later. One of the first significant developments in the evolution of vertebrates was the appearance of jaws. Early fish lacked jaws, which meant they could only feed by filtering small particles from the water. However, some of the fish that evolved later during the Cambrian period developed jaw-like structures that allowed them to capture and chew food more efficiently. This development made it possible for fish to feed on a wider range of organisms, including larger prey. The appearance of jaws also made it easier for these early fish to defend themselves against predators. The development of jaws was a major evolutionary step. With the ability to bite and chew, fish could now exploit different food sources and become more active hunters. This change also led to a wider variety of feeding strategies, including scavenging, hunting, and grazing. As fish became more specialized in their feeding habits, they were able to adapt to different environments and take on new roles in the ecosystem. Alongside the development of jaws, other important features began to evolve. Fish started to develop more advanced fins, which helped them swim more efficiently. These fins allowed the fish to steer and maintain balance in the water. Some fish evolved paired fins, which made it easier for them to move through the water in a controlled way. The evolution of these fins was a crucial step in the development of more advanced vertebrates that would eventually move on to land. The late Cambrian period also saw the emergence of early vertebrates that began to show signs of adapting to life in shallow waters. These fish had developed features that made them better suited for moving in and out of the water. They had more developed fins, which gave them more mobility in the shallows. This was an early precursor to the later evolution of animals that would leave the oceans and eventually become land-dwelling creatures. These fish were the first vertebrates to take steps toward a life on land, although it would take millions of years before vertebrates fully adapted to living outside the water. The transition from life in the oceans to life on land was one of the most significant steps in the history of life on Earth. The early vertebrates that lived during the Cambrian period were the first creatures to have the necessary structures to make this transition. They had a backbone, a nervous system, and fins, all of which would eventually help them adapt to life on land. The development of these features paved the way for the appearance of amphibians, the first vertebrates to live both in water and on land. The fish of the late Cambrian period were still simple compared to the diverse and complex vertebrates that would later appear. However, they were the first animals to show the key features that would become the foundation for all vertebrates. Their backbones provided support, while their nervous system allowed them to move and respond to their environment. As they developed jaws and more specialized fins, they became better suited for life in the seas and laid the groundwork for the evolution of more complex forms of life. The first vertebrates were a small but important step in the history of life. They helped shape the course of evolution by providing the foundation for more advanced creatures. These early fish were the ancestors of the vertebrates that would eventually evolve into land-dwelling creatures, including amphibians, reptiles, and mammals. The Cambrian period marked a turning point in the evolution of life on Earth, as vertebrates began to evolve the features that would eventually allow them to conquer new environments and diversify into the many forms we see today. Around 470 million years ago, the first simple plants began to appear on land. These plants were small and non-vascular, meaning they did not have the specialized tissues needed to transport water and nutrients over long distances. The earliest land plants were mosses and liverworts, small plants that would seem unremarkable to us today, but played a key role in shaping the Earth's early ecosystems. While they lacked the complex structures of modern plants, these early life forms were crucial for the development of terrestrial life. Before plants moved onto land, the Earth's surface was barren, and life was confined mostly to the oceans. The land was harsh and dry, and without plants to hold the soil in place, much of the Earth's surface would have been unstable. The arrival of plants was a turning point. These early land plants helped to stabilize the soil, creating the first steps toward ecosystems that could support more complex life. The first land plants did not look like the towering trees or vast fields of grass we think of today. Instead, they were tiny, low-growing plants that thrived in moist environments. These plants did not have roots, stems, or leaves like modern plants, which made them very different from the plants we are familiar with now. Instead, they absorbed water directly through their cells, much like modern mosses do. Despite their small size, they played a big role in the environment. Mosses and other early plants grew in dense mats that covered the ground. They could survive in areas where other organisms might not have been able to, such as on rocks or in damp shaded areas. Because they didn't have roots to anchor them into the soil, these early plants relied on the moisture in the air or the ground to survive. In the absence of vascular tissue to carry water through their bodies, they needed to grow close to water sources. These plants helped to shape the environment in several important ways. First, they helped prevent soil erosion. Before plants appeared, rain and wind could easily wash away the loose soil, leaving the land bare. However, the growth of mosses and liverworts helped to hold the soil in place. Their dense mats absorbed water, preventing the soil from being washed away. This was a critical development for the future of life on land, as it created more stable conditions where other organisms could eventually settle. In addition to holding the soil together, early land plants also played a role in the atmosphere. As they grew and reproduced, they contributed oxygen to the environment. The process of photosynthesis, where plants use sunlight to turn carbon dioxide and water into food, also produces oxygen as a byproduct. Even though these first plants were small and simple, they began to contribute to the oxygen levels in the atmosphere, setting the stage for the evolution of more complex life forms. The first land plants were not the only organisms to move onto land. They were soon joined by fungi, which formed important symbiotic relationships with plants. Fungi helped plants to absorb nutrients from the soil, while plants provided fungi with sugars produced through photosynthesis. This partnership was essential for the survival of early land plants, as the soil at this time lacked many of the nutrients that plants need to grow. These simple land plants did not just change the land itself. They also influenced the climate. The development of plants on land helped to regulate the Earth's temperature by absorbing carbon dioxide from the atmosphere. Carbon dioxide is a greenhouse gas which traps heat in the atmosphere. By removing carbon dioxide through photosynthesis, plants help to reduce the amount of heat trapped in the atmosphere, making the Earth cooler and more stable. Although the first land plants were small and simple, their appearance marked the beginning of a long and complex process that would eventually lead to the vast forests and diverse ecosystems that we are familiar with today. These early plants set the stage for the development of more complex plants with roots, stems, and leaves. Over time, plants would evolve to adapt to life on land, developing more advanced structures to survive in different environments. The evolution of land plants also had a profound impact on the creatures that would later inhabit the earth. As plants spread across the land, they created new habitats for animals. These early plants provided food and shelter for small invertebrates, which in turn created the foundation for more complex ecosystems. Eventually, more complex animals would evolve to take advantage of the resources provided by plants, including herbivores that fed on the plants themselves. Despite their simple nature, these early plants were a key development in the history of life on Earth. They were the first organisms to conquer the land, and their presence created conditions that allowed for more complex life forms to evolve. The growth of plants also had important effects on the atmosphere, the climate, and the soil, and helped to stabilize the environment in ways that would support more advanced ecosystems. The process of plant evolution on land was not a fast one. For millions of years, plants remained small and simple, with little change in their basic structure. But over time, as plants adapted to different environments, they began to evolve more specialized features. The appearance of roots, for example, allowed plants to anchor themselves into the soil and absorb water more effectively. The development of leaves allowed plants to capture more sunlight and produce more food through photosynthesis. These innovations set the stage for the rise of larger and more complex plants. By the end of the Silurian period, plants had already begun to diversify and spread across the land. Some plants grew larger and developed more complex vascular systems to transport water and nutrients. This allowed plants to grow taller and spread out over larger areas. These changes helped pave the way for the eventual appearance of larger plants and trees, leading to the creation of the first true forests. The first land plants were simple, but their importance cannot be overstated. They were the pioneers of life on land, and their presence helped shape the environment in ways that would allow more complex life forms to evolve. From these small, non-vascular plants grew the vast, diverse ecosystems that would support animals and plants for millions of years to come. While they were simple compared to the plants we see today, they played a crucial role in shaping the Earth's early ecosystems and setting the stage for the life that would follow. Around 420 million years ago, Earth witnessed a significant change with the appearance of the first land animals. These early land animals were arthropods, such as millipedes and early insects, which began to explore the land. However, the transition from water to land was not immediate. It was a gradual process that took millions of years. The adaptation to land presented challenges, and these early creatures had to evolve new features to survive outside the oceans. Before arthropods made their move onto land, the Earth's surface was still dominated by marine life. Plants had already begun to colonize the land, but animals were largely confined to the oceans. The first steps of land life were taken by creatures that already had ancestors in the water. Arthropods, like millipedes, already had many features that helped them live in the water, such as a hard exoskeleton and jointed legs, which allowed them to move efficiently. These early animals would gradually adapt to the land over millions of years, developing new traits to cope with the challenges of a terrestrial environment. The first arthropods to make the transition to land likely lived in moist environments, such as near water sources or in humid, sheltered places. These habitats provided the moisture needed to prevent desiccation or drying out, which was one of the main challenges animals faced when leaving the oceans. The land was much drier and more exposed to sunlight, making it difficult for animals with soft bodies to survive. Early arthropods, like millipedes, had already developed a hard exoskeleton, which helped to protect them from drying out and gave them the ability to move across the ground. One of the main advantages that arthropods had when they first moved onto land was their hard exoskeleton. The exoskeleton was made of a material called chitin, which is tough and resistant to water loss. This gave the arthropods a survival advantage, as it allowed them to venture onto land without losing too much moisture from their bodies. Over time, the exoskeleton would continue to evolve to become more efficient, providing better protection against predators and the environment. Another adaptation that helped early arthropods survive on land was their segmented bodies and jointed legs. These features made them more mobile and able to move across various types of terrain. The jointed legs allowed for more efficient movement and gave these animals the ability to crawl over rocks, soil, and plant matter. Their bodies were also segmented, which made it easier for them to bend and maneuver in tight spaces, such as in the cracks of rocks or under the cover of vegetation. Insects were some of the first animals to evolve flight, which further helped them adapt to life on land. While the first insects were likely small and simple, the development of wings opened up new possibilities for movement and survival. Insects could now fly away from predators, find new food sources, and travel between different habitats. Over time, the ability to fly would become a key feature in the success of insects, allowing them to spread across the globe. Despite their many advantages, early land animals faced several challenges. The land was a much more variable environment than the oceans. Temperature changes could be extreme, and the availability of water was not guaranteed. Animals that lived in the water were used to a stable environment, where temperature and salinity didn't change as much. On land, however, conditions could shift rapidly, and animals needed to find ways to cope with these changes. For early arthropods, one of the major challenges was the risk of desiccation. Without the constant moisture of the oceans, land was a much drier place. The air lacked the humidity of the oceans, and land animals had to evolve ways to prevent their bodies from drying out. The development of a hard exoskeleton, as mentioned earlier, helped arthropods to survive this challenge. However, over time, other adaptations, like internal water conservation mechanisms, evolved in these early land animals. Some of these animals, like early millipedes, also developed a way to breathe more efficiently, allowing them to live in environments with less available moisture. The transition to land also required changes in reproduction. In the water, animals could lay their eggs in the aquatic environment, where the water provided protection and the eggs were kept moist. On land, eggs needed to be protected from the dry air, so early land animals had to develop ways to keep their eggs safe. Some arthropods evolved to lay their eggs in moist environments, while others developed specialized protective coverings for their eggs, ensuring they would stay hydrated until they hatched. Another important adaptation for land animals was the development of specialized respiratory systems. In the oceans, animals could rely on the surrounding water for oxygen. On land, oxygen was more concentrated in the air, but animals still needed ways to breathe efficiently. Early land arthropods developed specialized structures like spiracles, small openings in their bodies that allowed air to enter. These structures allowed them to breathe while minimizing the loss of moisture from their bodies. Over time, more complex respiratory systems evolved to support larger, more active land animals. The gradual move onto land was not just a shift in habitat, it was a complete transformation in the way animals interacted with the environment. The land presented new opportunities, but also new dangers. Animals had to adapt to the dry conditions, the extreme temperatures, and the risk of desiccation. The development of exoskeletons, wings, and specialized respiratory systems allowed arthropods to thrive on land, but these were just the beginning. As the Earth's ecosystems evolved, more creatures would make the transition to land, eventually leading to the emergence of vertebrates and the rise of complex terrestrial ecosystems. While the early land animals were small and simple, they were a crucial part of the process that would eventually lead to more complex life forms. These arthropods helped to shape the land by breaking down organic matter, spreading plant pollen, and creating the foundation for more diverse ecosystems. As these early animals adapted to land, they paved the way for larger and more diverse groups of animals to follow. The transition from water to land was not quick, but over millions of years, it transformed the planet's ecosystems and set the stage for the rise of land. Dwelling creatures, including the dinosaurs and mammals, that would later dominate the Earth. The Devonian period, which lasted from 419 to 359 million years ago, is often called the Age of Fish because of the dramatic rise in the diversity and abundance of fish species. During this time, fish became the dominant vertebrates in Earth's oceans, and many new forms appeared, including the first fish with jaws. But the Devonian wasn't just about fish. It also saw the appearance of the first amphibians, creatures that could live both in water and on land. This period set the stage for the rise of vertebrates on land, a pivotal moment in the history of life on Earth. Fish were the stars of the Devonian period. The oceans were teeming with different types of fish, some of which were quite advanced compared to earlier species. The rise of jawed fish, like placoderms and early cartilaginous fish, marked a major step in fish evolution. Before this period, most fish were jawless, feeding on small particles of food by filtering the water. But the appearance of jaws allowed fish to catch and chew larger prey, opening up new food sources and creating a new level of competition in the oceans. The development of jaws gave fish an advantage in hunting and defense, helping them become more active and diverse. Fish in the Devonian came in many shapes and sizes. Some, like the placoderms, were heavily armored and looked similar to modern-day sharks, while others, like the lobe, finned fish, had more flexible bodies. These lobe, finned fish had fleshy fins that were different from the thin finned fish we see today. These fins allowed for more movement and flexibility, setting the stage for the evolution of amphibians. Lobe, finned fish were an important part of the Devonian oceans, but they would eventually give rise to the first vertebrates that could venture onto land. The Devonian was also a time when the first amphibians appeared. These early amphibians were a bridge between the world of water and land. They were vertebrates, like fish, but had developed features that allowed them to survive on land as well as in water. The first amphibians were likely descendants of the lobe, finned fish, which had already evolved the ability to breathe air through primitive lungs, in addition to using gills for underwater respiration. The first amphibians could move around on land but still depended on water for reproduction and for keeping their skin moist. Amphibians like Ichthyostega, one of the earliest known examples, were still very much tied to the water. They had limbs that allowed them to move on land, but they were not fully adapted for life on land yet. Their bodies were still heavy and clumsy, making it hard for them to walk long distances on land. Instead, they likely spent most of their time in shallow waters, using their limbs to push themselves along the bottom of rivers or lakes. As these amphibians adapted to life on land, they began to develop features that helped them survive in this new environment. For example, their lungs became more developed, allowing them to breathe air more efficiently. Their skin, which was once smooth and wet, began to develop more of a waterproof quality, helping them conserve moisture. But amphibians still needed water for reproduction, because their eggs didn't have the protective shells that later land animals would develop. They had to lay their eggs in water to prevent them from drying out, while fish were thriving in the oceans. Land plants were also undergoing significant changes during the Devonian. These plants were still simple, but were starting to grow taller and more complex. By this time, the first trees were emerging, creating forests in certain areas. These forests helped to change the environment, providing more moisture and shade, and creating new habitats for animals. These early plants were crucial for the development of amphibians, because they created an environment where land animals could begin to thrive. The rise of fish and amphibians during the Devonian also had an impact on the Earth's atmosphere. As plants grew taller and spread more widely, they began to produce more oxygen through photosynthesis. This increase in oxygen would eventually lead to the development of more complex life forms, including larger animals. The changes in the environment, driven by the rise of plants and animals, helped to set the stage for the next phase of evolution. As life began to move from the oceans to land, the Devonian period was a time of great change for life on Earth. Fish became the dominant vertebrates in the oceans, evolving into many new forms and becoming more specialized. The appearance of jawed fish allowed for new feeding strategies and hunting techniques, making fish more successful and diverse. But it was the first amphibians that truly marked the transition from life in the water to life on land. These creatures were the first to adapt to both environments, and their presence set the stage for the future evolution of vertebrates on land. While the first amphibians were not fully land-dwelling creatures, their adaptations were key to the eventual rise of more complex land vertebrates. Over millions of years, amphibians would evolve into reptiles, which were better suited for life on land. Reptiles, in turn, would give rise to mammals and birds, leading to the wide variety of vertebrates that we see today. The Devonian period, often called the Age of Fish, was a pivotal time in Earth's history. The oceans were filled with a diverse range of fish, and the first amphibians emerged as the first creatures to make the leap from water to land. This was just the beginning of a long process of adaptation and evolution that would eventually lead to the vast diversity of life on Earth. The Devonian laid the groundwork for the ecosystems we know today, with the rise of fish, amphibians, and the first land plants setting the stage for the land-dwelling animals that would follow. In the late Devonian period, a remarkable shift occurred in the evolution of life on Earth. Amphibians, including early tetrapods, evolved from fish and began to colonize the land. These amphibians were the first vertebrates to make the move from water to land, marking a key moment in the history of life. They were the ancestors of all modern land vertebrates, including reptiles, birds, and mammals. The transition from water to land was not a sudden event. It took millions of years for early fish to develop the traits necessary to live on land. The first tetrapods were lobe-finned fish, a group of fish that already had fleshy fins, which were more flexible and robust than the fins of modern fish. These fish were well adapted to life in shallow, swampy waters, where the water levels often fluctuated, leaving pools of water that became disconnected from the main body of water. In these habitats, the need for mobility and the ability to move across the land, even briefly, likely became important. These early fish already had features that would help them adapt to life on land. The fleshy, lobe-like fins were supported by bones, similar to the limbs of land vertebrates. This structure was a precursor to the limbs of tetrapods. At first, these fins were used for propulsion in the water, but over time they began to evolve into more limb-like structures capable of supporting the fish's body weight on land. The earliest tetrapods, such as Ichthyostega and Acanthostega, were not fully adapted to life on land. They still had strong ties to aquatic life. These creatures had limbs that allowed them to move in shallow water and on the land, but they were not well suited for sustained life on land. They likely spent a significant amount of time in the water, using their limbs to navigate through shallow pools or swampy environments. Their bodies were still heavy, and their lungs were not as well developed as those of later amphibians. These early tetrapods had to breathe air, but still depended on the water to keep their skin moist and for reproduction. The movement onto land presented several challenges. The air was dry compared to the water, and animals had to evolve ways to prevent their bodies from drying out. Early amphibians, like their fish ancestors, had to develop a waterproof barrier on their skin to retain moisture. They also needed to adapt to breathing air and their lungs began to develop more efficiently for extracting oxygen from the atmosphere. Despite these challenges, the evolution of limbs and lungs allowed amphibians to explore new environments and fill ecological niches that were previously unavailable to aquatic life. On land, they had fewer predators to contend with, and the air offered an abundant source of oxygen. As these creatures began to leave the water more frequently, they also began to exploit terrestrial resources, such as plants and insects. Early amphibians were still reliant on water for reproduction. Their eggs were soft and lacked the protective shells seen in later land vertebrates. Like fish, they had to lay their eggs in water to prevent them from drying out. However, their ability to move onto land and breathe air made them some of the first animals to experience life outside of the aquatic environment, setting the stage for further adaptations that would eventually lead to the evolution of fully terrestrial vertebrates. The development of limbs allowed these early tetrapods to explore a variety of environments, including wet and dry areas. Over time, amphibians evolved into creatures that could spend more time on land. These early land-dwelling amphibians were still linked to water, but they had begun to show signs of being able to move more freely on land, a crucial step toward the evolution of reptiles and other fully terrestrial animals. During the late Devonian, the Earth's climate was changing, and forests were starting to take shape. These new environments provided additional challenges and opportunities for early amphibians. The rise of plants and the spread of forests created new habitats, offering food sources like insects and vegetation, which amphibians could exploit. The growing forests also helped stabilize the environment, providing shelter and moisture for these early land animals. As amphibians continued to evolve, they developed more advanced features that helped them fully transition to life on land. Their lungs became more efficient at extracting oxygen, and their skin became better suited for living in a dry environment. Over time, amphibians became more specialized, with some becoming better adapted to living in the water, while others began to move more freely on land. These adaptations laid the groundwork for the eventual rise of reptiles, which were fully adapted to life on land. In terms of reproduction, amphibians were still bound to water for breeding. Their eggs, like those of their ancestors, lacked the hard shells that would later evolve in reptiles. The soft jelly, like eggs, needed to be laid in water to prevent desiccation. However, the gradual development of more complex structures and systems within amphibians, such as stronger, more resilient skin and better lungs, helped them survive for longer periods on land. Eventually, these amphibians would give rise to reptiles, whose eggs had protective shells, allowing them to reproduce on land and further reduce their reliance on aquatic habitats. The rise of amphibians marked the beginning of the age of terrestrial vertebrates. They were the first creatures to venture out of the oceans and explore life on land. Though they still relied on water in many ways, amphibians paved the way for the evolution of reptiles and later mammals and birds. The features that emerged in these early tetrapods, limbs, lungs, and skin adaptations, were crucial for the development of land-dwelling creatures that would become the dominant vertebrates on Earth. The Devonian period was a time of tremendous evolutionary change. Fish, which had dominated the oceans for hundreds of millions of years, gave rise to the first amphibians, which began to explore the land. These amphibians were the ancestors of modern land vertebrates, and their emergence set the stage for the complex ecosystems we would later see on land. Their ability to breathe air, move with limbs, and gradually adapt to terrestrial life marked a turning point in the history of life on Earth, one that would shape the course of evolution for millions of years to come. During the Carboniferous period, which lasted from about 359 to 299 million years ago, Earth was a very different place. The landscape was dominated by vast swampy forests of ferns, giant club mosses, and horsetails. These lush green forests stretched across much of the land, creating an environment that was ideal for plant and animal life. In these forests, the atmosphere was rich in oxygen, which allowed for the development of some of the largest arthropods the planet has ever seen, including giant millipedes and enormous dragonflies. The Carboniferous period followed the Devonian and saw a boom in plant life. The warm, humid climate created the perfect conditions for plants to thrive. Large ferns, club mosses, and horsetails grew to impressive sizes, forming dense forests that covered much of the Earth's surface. These plants were among the first to create the large-scale ecosystems that would become the foundation for the Earth's later plant and animal life. The Carboniferous forests were the ancestors of the modern day forests we are familiar with, but they were much denser and more tropical. As plants flourished, the Earth's atmosphere became much more oxygen-rich. This increase in oxygen had a significant impact on the life forms of the time. Higher oxygen levels allowed for the evolution of much larger animals, especially arthropods. These creatures, which include insects and crustaceans, were able to grow to sizes far beyond what we see today, due to the higher oxygen content. The larger oxygen intake allowed them to support bigger bodies and more complex structures. Among the most impressive creatures of the Carboniferous period were the arthropods. Giant millipedes roamed the forest floors, growing to lengths of over 8 feet. These massive arthropods were part of a diverse group of creatures that helped shape the ecosystems of the time. Their size was largely a result of the high oxygen levels in the atmosphere, which allowed them to grow larger than any millipedes alive today. These creatures played an important role in breaking down dead plant material, helping to recycle nutrients back into the soil. Along with the giant millipedes, dragonflies were another large arthropod species that flourished. During this time, these dragonflies had wingspans of up to 2.5 feet, making them much larger than the dragonflies we see today. The larger size of these insects allowed them to fly more efficiently and enabled them to become top predators in the skies. These giant dragonflies fed on smaller insects and even other arthropods, playing a key role in maintaining balance in the ecosystem. The abundance of plant life during the Carboniferous period also had a huge impact on the development of land ecosystems. As the forests expanded, they provided food and shelter for a variety of creatures. The plants themselves also helped shape the landscape. Ferns and other plants were able to grow quickly in the swampy, waterlogged soil, which created a rich environment for plant-eating animals like herbivorous arthropods. Over time, these plants began to decay and form vast peat bogs, which would eventually become the coal deposits we use today for fuel. The Carboniferous forests were not only a place for plants and arthropods to thrive, but they also saw the rise of early amphibians and reptiles. Amphibians, which had evolved from fish during the Devonian, were some of the first vertebrates to venture onto land. By the Carboniferous, amphibians had evolved into larger, more complex creatures. They still needed water to reproduce, but many had developed the ability to move across land more efficiently. Some amphibians even began to evolve into the first reptiles, marking the beginning of the transition to fully terrestrial life for vertebrates. The presence of large plants, such as the towering ferns and club mosses, created an environment where early reptiles could find food and shelter. These first reptiles were an important step in the evolution of life on Earth. Unlike amphibians, reptiles were not tied to water for reproduction. They developed the ability to lay eggs with hard protective shells, which allowed them to reproduce on land. This adaptation helped reptiles expand into a variety of new habitats, paving the way for the development of more complex ecosystems in the years to come. The combination of plant growth, increased oxygen levels, and the evolution of new types of animals created a unique environment during the Carboniferous period. The vast swampy forests became home to not only plants and arthropods, but also early amphibians and reptiles, all of which played a role in shaping the ecosystems of the time. These ecosystems would eventually give rise to more complex forms of life and lay the groundwork for the later development of the dinosaurs and mammals. While the Carboniferous period is often associated with the rise of large arthropods and the spread of dense forests, it was also a time of significant geological change. The period saw the formation of large land masses, including the supercontinent Pangaea, which would eventually become the foundation for the continents we recognize today. The climate, which was warm and humid during the Carboniferous, began to change toward the end of the period. As the continents shifted and the climate cooled, the dense forests began to diminish, leading to a change in the types of plants and animals that would thrive in the coming periods. The Carboniferous period was a time of growth, change, and adaptation. The rise of swampy forests, the evolution of large arthropods, and the appearance of early amphibians and reptiles all marked a turning point in the history of life on Earth. These developments set the stage for the evolution of more complex life forms in the future. The forests and creatures that flourished during this time were the ancestors of many of the ecosystems and life forms that we see today. While the world of the Carboniferous was vastly different from our own, it was a critical period in the evolution of life on Earth. By the late Paleozoic, around 300 million years ago, Earth's land masses began to converge. This movement brought together nearly all of the planet's continents to form a massive supercontinent known as Pangaea. Before this, Earth's continents were scattered across the globe, moving slowly due to the shifting of tectonic plates beneath them. Over millions of years, these land masses gradually collided and fused, creating Pangaea, a giant landmass that dominated the planet. This event occurred just before the age of dinosaurs, setting the stage for the changes that would follow. Pangaea's formation was a slow and gradual process. The Earth's tectonic plates are in constant motion, but they move at a very slow pace. As the plate shifted, they caused continents to collide. For example, parts of what are now Africa and Europe began to come together, while North America moved toward what is now Greenland. These collisions didn't happen all at once, but over tens of millions of years, the land masses were drawn closer together. By the time Pangaea had formed, it was one continuous landmass that stretched across the equator. The formation of Pangaea had a profound impact on Earth's climate and ecosystems. Before the supercontinent came together, the planet's climate was more varied, with different landmasses experiencing different weather patterns. Once Pangaea formed, however, Earth's climate became more extreme. The vast landmass created both larger inland areas and more isolated coastal regions. With so much land massing together, there were fewer areas of ocean to moderate temperatures. This led to more dramatic temperature swings, with the interior of Pangaea likely becoming much hotter in the summer and colder in the winter, as the oceans could no longer regulate the land's climate as effectively. On the coasts of Pangaea, new types of ecosystems began to develop. The vast landmass created more inland regions, which may have been drier and less hospitable for life. But along the edges of Pangaea, where the land met the oceans, new opportunities for life arose. The convergence of the continents also led to the creation of mountain ranges, like the Appalachian Mountains in what is now North America, which impacted the flow of air and water, further shaping the climates of these regions. The formation of Pangaea also meant that many previously separated species of plants and animals began to come into contact with each other. Before Pangaea formed, the continents had been isolated for millions of years, leading to the evolution of different species on each landmass. But as the continents merged, animals and plants from different regions came into contact, often leading to new interactions, competition, and even new evolutionary paths. This massive land connection allowed species to spread across the supercontinent, sometimes leading to the mixing of ecosystems. For example, some species of early amphibians and reptiles that had evolved in one part of the world now found themselves living in new, unfamiliar environments as Pangaea formed. This allowed for the exchange of species across the supercontinent. However, some species found themselves in new climates and conditions that forced them to adapt, or they went extinct. This process of change and adaptation marked the beginning of the Mesozoic era, which would be the age of the dinosaurs. The formation of Pangaea also influenced Earth's oceans. With such a large landmass, the oceans became more divided. The interior of Pangaea was far from the oceans, meaning it became more dry and less hospitable for marine life. The seas that surrounded the supercontinent were isolated from one another, and over time, this created different marine environments and habitats. As a result, the animals living in these seas had to adapt to the changes. Many species that had thrived in the more open seas now found themselves restricted to smaller, isolated bodies of water. The process of Pangaea's formation was not the end of continental movement. Over millions of years, the supercontinent began to break apart. The very same tectonic forces that had pulled the continents together now began to pull them apart. The forces of plate tectonics, which are responsible for moving the Earth's landmasses, slowly began to create rifts in Pangaea. These rifts expanded over time, causing Pangaea to fragment into smaller landmasses, eventually leading to the formation of the continents as we know them today. While Pangaea existed for only a relatively short time in the context of Earth's history, its formation marked an important chapter in the development of life on Earth. The land connections between continents allowed species to spread across vast distances, which increased biodiversity. But it also led to new challenges, as life had to adapt to the changing climates and the mixing of ecosystems. The rise of Pangaea also set the stage for major evolutionary events. By the time the supercontinent was fully formed, life on Earth was changing rapidly. Early amphibians and reptiles were thriving, and the stage was set for the appearance of the dinosaurs. These land-dwelling creatures would dominate the planet for millions of years, evolving into many different forms and occupying a variety of ecological niches. Pangaea, with its vast interconnected landmasses, played a key role in the development of these species and the ecosystems in which they lived. The collision of continents that formed Pangaea also led to the formation of mountain ranges, like the Appalachians, which had a lasting effect on Earth topography. These mountain ranges not only changed the physical landscape, but also had an impact on weather patterns, river systems, and the distribution of species. These geographic features would continue to shape life on Earth for millions of years. Pangaea's formation and eventual breakup were part of the continuous cycle of continental drift. The tectonic plates beneath Earth's surface are always moving, shifting continents in slow but dramatic ways. As Pangaea came together, it reshaped Earth's environments, creating new habitats, altering climates, and fostering new opportunities for life. Over time, as the supercontinent began to break apart, it set the stage for the continents we recognize today. These shifting landmasses created the dynamic and ever-changing planet that we live on, where life is constantly adapting to new conditions.